Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky. Exploring the Goldilocks Zone and the search for habitable worlds. The concept of the Goldilocks Zone is one of the most intriguing and significant ideas in the search for extraterrestrial life. This term refers to the habitable zone around a star where conditions are just right for liquid water to exist on the surface of a planet. Not too hot, not too cold, but just right. The idea takes its name from the children's story Goldilocks and the Three Bears, where Goldilocks finds the porridge that is neither too hot nor too cold, but just right. In astronomical terms, finding a planet in the Goldilocks zone is one of the primary criteria for identifying potentially habitable worlds. This narrative delves into the origins, significance, and ongoing search for planets within the Goldilocks zone. The search for habitable worlds beyond Earth has captivated scientists and the public alike for centuries. Early astronomers, using rudimentary telescopes, could only speculate about the possibility of other planets hosting life. It wasn't until the late 20th and early 21st centuries, with the advent of advanced telescopes and space missions, that the search for exoplanets, planets orbiting stars other than our Sun, became a rigorous scientific endeavor. The Goldilocks Zone concept emerged as a critical framework in this quest, providing a way to prioritize the search for planets that might have the right conditions for life as we know it. Liquid water is considered essential for life based on our understanding of biology on Earth. It serves as a solvent for biochemical reactions, a medium for nutrient transport, and a component of cells. Thus, the presence of liquid water on a planet is seen as a strong indicator of its potential habitability. The Goldilocks zone is defined by the range of distances from a star where the temperature allows for liquid water to exist. If a planet is too close to its star, it will be too hot, causing any water to evaporate. Conversely, if a planet is too far, it will be too cold, causing any water to freeze. The exact boundaries of the Goldilocks zone vary depending on several factors, including the type and size of the star and the planet's atmosphere. For example, the Sun's Goldilocks zone extends roughly from the orbit of Venus to just beyond Mars. Earth, conveniently located within this zone, has a surface temperature range that allows liquid water to persist, supporting a diverse range of life forms. The discovery of exoplanets has significantly expanded our understanding of the Goldilocks zone. The first confirmed exoplanet orbiting a main sequence star, 51 Pegasi b, was discovered in 1995. This gas giant, however, is not within its star's Goldilocks zone. Over the years, astronomers have identified thousands of exoplanets using various detection methods, such as the radial velocity method and the transit method. The Kepler Space Telescope, launched in 2009, has been particularly instrumental in this search, discovering thousands of potential exoplanets, some of which reside in the habitable zones of their stars. One of the most exciting discoveries in the search for habitable exoplanets is Kepler-186f, located about 500 light-years away in the constellation Cygnus. This Earth-sized planet orbits within the habitable zone of its star, Kepler-186, a cooler, red dwarf star. While it remains unknown whether Kepler-186f has liquid water, its location in the habitable zone makes it a prime candidate for further study. Similarly, the TRAPPIST-1 system, located about 40 light-years away, has 7 Earth-sized planets, 3 of which are within the star's habitable zone. These planets offer tantalizing opportunities for studying potentially habitable worlds around a single star. The Goldilocks Zone is not a static concept. It evolves with our understanding of planetary science and astrobiology. For instance, a planet's atmosphere can significantly influence its habitability. Greenhouse gases like carbon dioxide and methane can trap heat, extending the habitable zone further from the star. Conversely, a lack of atmosphere or a thin atmosphere, like that of Mars, can lead to rapid heat loss, making a planet less hospitable even if it is within the traditional habitable zone. Additionally, geological activity and magnetic fields can play crucial roles in maintaining habitable conditions by recycling nutrients and protecting the planet from harmful stellar radiation. While the presence of liquid water is a key criterion for habitability, it is not the only factor. Scientists also consider the stability of the star and the planet's orbit. Stable stars with long lifespans, like our Sun, provide a consistent energy source, giving life the time to develop and evolve. Planets with stable, nearly circular orbits are less likely to experience extreme temperature fluctuations, which could disrupt the potential for life. The interaction between a planet and its star is complex, and many variables must align to create a truly habitable world. The search for habitable exoplanets extends beyond merely locating them within the Goldilocks zone. Advanced telescopes and instruments are now focusing on characterizing the atmospheres of these planets. By analyzing the light that passes through or is reflected by a planet's atmosphere, scientists can identify its chemical composition. This technique, known as spectroscopy, can reveal the presence of water vapor, oxygen, methane, and other gases that could indicate biological processes. The James Webb Space Telescope, set to launch soon, is expected to play a pivotal role in this atmospheric characterization. The search for extraterrestrial life is not confined to exoplanets. Moons within our own solar system, such as Europa and Enceladus, also offer promising environments for life. These icy moons, despite being outside the traditional habitable zone, have subsurface oceans kept liquid by tidal heating from their parent planets. The discovery of plumes of water vapor erupting from Enceladus has sparked interest in the potential habitability of these moons. The exploration of these and other moons by future missions could provide valuable insights into the conditions required for life and expand our understanding of habitable environments. The concept of the Goldilocks Zone has profound implications for the broader field of astrobiology and our place in the universe. The discovery of potentially habitable exoplanets raises fundamental questions about the prevalence of life beyond Earth. Are we alone, or is life a common phenomenon in the cosmos? The answers to these questions could reshape our understanding of life's origins and its distribution across the universe. The search for habitable worlds is not just a scientific endeavor but also a philosophical and existential quest to understand our place in the cosmos. The quest to find planets within the Goldilocks Zone has also driven technological advancements and international collaboration. The development of sophisticated telescopes, both ground-based and space-based, has pushed the boundaries of what we can observe and detect. International consortia and space agencies have joined forces to fund and operate these ambitious projects, recognizing that the search for extraterrestrial life is a global endeavor. The sharing of data and resources across borders has accelerated discoveries and fostered a sense of unity in the scientific community. Public interest and engagement in the search for habitable exoplanets have also played a significant role. The discovery of Earth-like planets in the habitable zones of distant stars captures the imagination and inspires curiosity. Outreach programs, citizen science projects, and educational initiatives help bring the excitement of these discoveries to a broader audience, encouraging future generations to pursue careers in science and astronomy. The fascination with finding another Earth fosters a collective sense of wonder and a desire to explore the unknown. As our technology and understanding of planetary systems continue to evolve, the criteria for habitability may expand beyond the traditional Goldilocks zone. The discovery of extremophiles, organisms that thrive in extreme conditions on Earth, suggests that life can exist in a wide range of environments. This has led scientists to consider the potential for life in more diverse and unconventional habitats, such as planets with thick atmospheres that retain heat, or rogue planets drifting through space with internal heat sources. The future of the search for habitable worlds will likely involve a combination of methods and technologies. Direct imaging, which involves capturing pictures of exoplanets by blocking out the light of their parent stars, is becoming increasingly feasible with the development of advanced coronagraphs and star shades. These technologies will allow astronomers to study the surfaces and atmospheres of exoplanets in greater detail, providing more direct evidence of their potential habitability. In addition to observational techniques, theoretical models and simulations play a crucial role in understanding the conditions necessary for life. By modeling planetary climates, atmospheric chemistry, and potential biosignatures, scientists can predict the types of environments where life might thrive. These models guide observations and help interpret the data collected from telescopes, offering insights into the complex interplay of factors that contribute to habitability. The search for life in the universe is a dynamic and evolving field. New discoveries continually challenge our assumptions and expand our horizons. The detection of planets around different types of stars, such as red dwarfs and binary systems, broadens the range of environments where we might find life. Each discovery adds a piece to the puzzle of understanding the diversity and potential of habitable worlds. The Goldilocks Zone remains a central concept in this quest, providing a framework for identifying the most promising candidates for habitability. As we continue to explore the universe, the discovery of another Earth-like planet and the habitable zone of its star would be a monumental achievement, offering the tantalizing possibility of finding life beyond our solar system. The narrative of the Goldilocks Zone is one of exploration, discovery, and the relentless pursuit of knowledge. It is a story that reflects humanity's innate curiosity and our desire to understand our place in the cosmos. From the early speculations of ancient astronomers to the cutting-edge research of today, the search for habitable worlds has driven technological advancements, fostered international collaboration, and captured the public's imagination. As we look to the future, the search for habitable planets within the Goldilocks Zone continues to push the boundaries of our scientific capabilities and our understanding of the universe. The discoveries we make along the way will not only illuminate the conditions necessary for life but also enhance our understanding of planetary systems, the formation and evolution of planets, and the potential diversity of life forms that might exist in the cosmos. Our journey began with the recognition that Earth occupies a unique position in the solar system where liquid water can exist, making it a haven for life as we know it. This realization spurred the search for other such locations in the vast expanse of space. The Goldilocks Zone, therefore, became a guiding principle, directing our telescopes and missions to regions where the conditions might be just right for life to thrive. The pace of discovery in this field has been astounding. Each year brings new exoplanetary candidates, some of which are tantalizingly Earth-like. For instance, the detection of Proxima Centauri b, orbiting the closest star to our solar system, within the habitable zone, has generated significant excitement. Although we still know little about its atmosphere and surface conditions, its proximity makes it a prime target for future observation and study. While Proxima Centauri b and other nearby exoplanets are high-priority targets, the search for habitable worlds extends much further into the galaxy. Missions like the Transiting Exoplanet Survey Satellite, TESS, and the future Plato mission by the European Space Agency aim to identify and study exoplanets around the nearest and brightest stars. These missions increase our chances of finding habitable planets that are close enough to allow for detailed follow-up observations. The challenge of characterizing exoplanets within the Goldilocks Zone requires innovative approaches and technologies. Spectroscopy, which involves analyzing the light from these planets, is crucial for determining their atmospheric composition and surface conditions. By studying the spectra of exoplanet atmospheres, scientists can detect the presence of key molecules such as water vapor, oxygen, carbon dioxide, and methane. These molecules can provide clues about the planet's potential to support life. One of the most exciting developments in this field is the advent of the James Webb Space Telescope, JWST. JWST's powerful instruments are designed to study the atmospheres of exoplanets in unprecedented detail. By observing the transits of exoplanets across their parent stars and analyzing the starlight that filters through their atmospheres, JWST can reveal the chemical fingerprints of various gases. This capability will be instrumental in assessing the habitability of planets within the Goldilocks Zone. As our observational techniques improve, we are also developing more sophisticated theoretical models to interpret the data we collect. These models simulate planetary climates and atmospheres under different conditions, helping us understand how various factors, such as distance from the star, atmospheric composition, and geological activity, influence a planet's habitability. For instance, models can predict how the greenhouse effect might warm a planet's surface or how volcanic activity might replenish its atmosphere. The study of extremophiles on Earth has broadened our understanding of the potential for life in diverse and harsh environments. These organisms thrive in conditions once thought to be inhospitable, such as deep ocean hydrothermal vents, acidic hot springs, and the frozen tundra of Antarctica. The resilience of extremophiles suggests that life might exist in a variety of forms and places, expanding the scope of the Goldilocks Zone beyond the traditional criteria. This realization has led scientists to consider other potential habitable environments in our solar system and beyond. For example, the icy moons of Jupiter and Saturn, such as Europa and Enceladus, have subsurface oceans beneath their frozen crusts. These oceans are kept liquid by tidal heating, which could provide the energy needed for life. Future missions, like the Europa Clipper, aim to explore these moons and search for signs of life, demonstrating that habitable zones can exist in unexpected places. The search for habitable exoplanets is not just about finding places where life might exist, but also about understanding the fundamental processes that make a planet habitable. This knowledge can inform our understanding of Earth's own habitability and the conditions that allowed life to flourish here. By studying other worlds, we gain insights into the delicate balance of factors that sustain life and the potential threats to planetary habitability. The implications of finding another habitable planet, or even life, are profound. Such a discovery would have far-reaching consequences for our understanding of biology, evolution, and our place in the universe. It would prompt us to reconsider the uniqueness of life on Earth and the possibility that life might be a common occurrence throughout the cosmos. The philosophical and existential questions raised by such a discovery would be as significant as the scientific ones. Each new discovery, whether it is a potentially habitable exoplanet or a better understanding of the factors that make a planet livable, brings us closer to answering some of the most profound questions we can ask. Is life common in the universe? What are the conditions that allow life to thrive? The narrative of the Goldilocks Zone is a story of hope and possibility. It is a reminder that the universe is vast and full of potential, and that our quest to find other habitable worlds is just beginning. As we explore the cosmos, we are not only searching for other places where life might exist, but also seeking to understand the fundamental nature of life itself and the conditions that make it possible. The future of the search for habitable planets within the Goldilocks Zone is bright, with new missions and technologies on the horizon. The next generation of telescopes and space missions promises to bring us closer to finding another Earth-like planet and perhaps even detecting signs of life. These advancements will continue to expand our understanding of the universe and our place within it. In conclusion, The Goldilocks Zone represents one of the most exciting and promising areas of study in modern astronomy. The search for habitable worlds within this zone is driven by our desire to find life beyond Earth and to understand the conditions that make a planet livable. As we continue to explore the cosmos, we are guided by the principles of scientific inquiry, technological innovation, and a shared sense of wonder. The discoveries we make along the way will not only illuminate the conditions necessary for life, but also enhance our understanding of the universe and our place within it. The journey to find habitable worlds is a testament to the resilience of the human spirit and our unending desire to explore, discover, and understand the cosmos.